Welcome to this problem walkthrough. Today, we'll tackle LeetCode problem number 841, Keys in Rooms. In this problem, we explore a scenario where we need to determine if all rooms can be visited starting from room 0, given the keys available in each room. Let's dive in and break it down step by step. In this problem, you are given a number of rooms, labeled from 0 to N1. Each room contains a list of keys, and these keys unlock other rooms. Specifically, if you are in room I, the keys in rooms I indicate which other rooms you can unlock. At the start, you are placed in room 0, which is already unlocked, and the rest of the rooms are locked. The goal is to determine whether you can visit every single room starting from room 0. If it's possible to visit all the rooms, you return true, otherwise, you return false. The input is represented as a list of lists, where each inner list corresponds to the keys in one room. The output is a Boolean value that answers the question, can all rooms be visited? Let's look at an example to better understand the problem. Suppose the input is rooms equals 1, 2, 3. Here, room 0 contains the key to room 1 contains the key to room 2, and room 2 contains the key to room 3. Room 3 has no keys. Starting in room 0, you use the key to enter room 1, then use the key in room 1 to enter room 2, and finally use the key in room 2 to enter room 3. Since all rooms have been visited, the output is true. Another example is rooms equals 1, 3, 3, 0, 1, 2, 0. Here, room 0 contains keys to rooms 1 and 3. Room 1 has keys to rooms 3, 0, and itself. Room 2 contains keys to room 2, and room 3 contains the key to room 0. However, in this case, room 2 is never accessed, so the output is false. Now, consider the example where rooms equals 2, 1. In this case, room 0 contains the key to room 2, and room 2 contains the key to room 1. Room 1 has no keys. Starting in room 0, you can use the key to access room 2, then use the key in room 2 to access room 1. Since all rooms have been visited, the output is true. The problem can be solved by ensuring that every room is reachable from room 0 using the keys you collect. If there exists at least one room that cannot be reached, the output will be false. The problem comes with constraints that help define its scope. The number of rooms, n, is given by the length of the input list, and it ranges from 2 to 10,000. Each room can contain up to 1,000 keys, and the total number of keys across all rooms does not exceed 30,000. Additionally, all keys in a single room are unique, and each key is a valid room index between 0 and N1. These constraints ensure that the input is well-formed and bound within reasonable limits for computational purposes. Edge cases include scenarios like having only one room, where you can already access it, or having disconnected keys that make some rooms permanently inaccessible. Some specific edge cases to consider include minimal input, such as rooms equals, where the second room cannot be accessed because no keys are available, resulting in false. Another edge case is having a single room, like rooms equals, which is already accessible, so the output is true. In cases of cyclic key distribution, such as rooms equals 1, 0, all rooms can be visited because the keys form a cycle. Lastly, disconnected keys, like in rooms equals 1, 3, make some rooms inaccessible, leading to a false result. These examples illustrate how different configurations of keys affect the ability to visit all rooms. To solve the keys in rooms problem, we can think of it as a graph traversal exercise. Here, each room acts as a node, and the keys inside a room represent directed edges to other rooms. One straightforward way to approach this is through a brute force method using backtracking. The idea is to start from room 0 and recursively explore all the rooms by using the keys we collect. To avoid unnecessary cycles, we maintain a visited array to track which rooms have already been accessed. The recursive function explores each room, marking it as visited, and then uses the keys in that room to move further. At the end of the traversal, we simply check if all rooms have been marked as visited. While this method is simple and intuitive, it has some downsides. For example, despite its linear time complexity of O, n plus e, where n is the number of rooms and e is the total number of keys, it can result in redundant checks for rooms that have already been visited. Additionally, it uses space for both the recursion stack and the visited array, which can make it less efficient for deeply nested graphs. An optimized approach to solving this problem is to use breadth-first search, or BFS. Instead of relying on recursion, BFS uses a queue to process rooms iteratively, making the traversal more systematic. To implement this, we start with a visited set to track the rooms we've already explored and a queue to manage the exploration process. We begin with room 0, mark it as visited, and add it to the queue. Then, as long as the queue isn't empty, we dequeue a room and use the keys in that room to visit other rooms that haven't been visited yet. The process continues until the queue is empty. At the end, we simply check if the number of visited rooms matches the total number of rooms. This approach still has a time complexity of O, n plus e, but it avoids the overhead of recursion by using an iterative method. Additionally, the space complexity is efficient, with memory used for the visited set and the queue. BFS is particularly advantageous because it explores rooms level by level, avoiding the inefficiencies of revisiting already explored rooms, and it handles deeply nested graphs more effectively than recursive methods. Another optimized method is an iterative version of depth-first search, or DFS. This approach builds on the intuition of the brute force DFS but avoids recursion by utilizing a stack. Here, we use a visited set to track the rooms we've already explored and a stack to manage the exploration process. We start by marking room 0 as visited and pushing it onto the stack. Then, while the stack is not empty, we pop a room from the stack and use the keys found in that room to visit other rooms that haven't been visited yet. Like BFS, we check at the end if the size of the visited set equals the total number of rooms. This iterative DFS approach has a time complexity of O, n plus e, and uses space for the visited set and the stack. While it avoids recursion-related issues like stack overflow, it may still be less efficient than BFS when dealing with deeply nested graphs, as it doesn't inherently prioritize breadth-first exploration. However, it's a solid alternative for those who prefer DFS but want to avoid the pitfalls of recursion. For this problem, we've chosen the optimized BFS approach as our preferred strategy. BFS offers a clean, iterative method for exploring rooms level by level. This systematic exploration avoids redundant checks and recursion-related overhead, making it a memory-efficient solution. One of the key advantages of BFS is its queue-based structure, which is easy to debug and understand, especially for iterative traversal problems. While DFS and BFS share the same time complexity of O, n plus e, BFS is particularly well suited for handling deeply nested graphs where recursion might fail due to stack limits. By balancing simplicity, efficiency, and memory usage, BFS emerges as a robust choice. Although the queue may require additional memory in some cases, its level order exploration ensures that memory usage remains manageable. In summary, graph traversal techniques like DFS and BFS are both viable for solving this problem, but BFS stands out for its iterative nature, systematic exploration, and ability to handle complex graph structures without the risks associated with recursion. In the keys and rooms problem, you are tasked with determining if it's possible to visit all rooms starting from room 0. Each room contains keys that unlock other rooms, and the arrangement of these keys can be thought of as a graph. Here, each room is a node, and the keys inside a room represent directed edges to other nodes. The challenge is to see if all nodes in this graph are reachable from the starting node, which is room 0. This framing allows us to apply graph traversal techniques to solve the problem efficiently. To solve this problem, we start by representing it as a graph using an adjacency list. Each room corresponds to a node, and the list of keys in a room points to the nodes it can reach. Next, we initialize some data structures. A visited set or array helps us keep track of which rooms we've already explored, ensuring we don't revisit them unnecessarily. We also use a stack or queue to manage the traversal process. A stack is ideal for depth-first search, DFS, while a queue is suitable for breadth-first search, BFS. After setting this up, we begin the traversal from room 0. Room 0 is marked as visited and added to the stack or queue, which we will process iteratively. During the traversal, we process each room by examining the keys it contains. For the current room, we retrieve its list of keys, which correspond to the adjacent nodes in the graph. For each key, we check whether the corresponding room has been visited. If it hasn't, we mark it as visited and add it to the stack or queue for further exploration. Once the traversal is complete, we check the visited set or array to ensure that all rooms have been visited. If every room is accounted for, we return true. Otherwise, we return false, indicating that some rooms are inaccessible from room 0. This problem leverages key insights from graph theory. The rooms in keys form an unweighted directed graph, making traversal algorithms like DFS and BFS highly applicable. DFS is particularly useful here as it explores as far as possible down a path before backtracking, and it can be implemented recursively for simplicity. BFS, on the other hand, processes all neighbors level by level, which can also work. In terms of efficiency, each key is processed at most once during the traversal, so the time complexity is proportional to the total number of keys, denoted as E. The space complexity is determined by the number of rooms, n, and the memory required for the recursion stack or queue. Several data structures play a crucial role in solving this problem. First, the adjacency list is used to represent the graph, where each room directly maps to its list of keys. This structure allows efficient access to a room's neighbors. Second, the visited array or set ensures we don't revisit rooms, preventing infinite loops and redundant work. Lastly, the stack or queue facilitates the graph traversal process. The stack is used for depth-first search, which delves deep into one branch before exploring others, while the queue is used for breadth-first search, which explores all neighbors at a given depth before proceeding deeper. Let's walk through an example using the input rooms equals 13, 301, 2, 0. Here, the adjacency list is already provided. We start by initializing an empty visited set and a stack containing only room 0. First, we pop room 0 from the stack, mark it as visited, and add its keys, 1, 3, to the stack. Next, we pop room 3, mark it as visited, and add its keys. Since room 0 is already visited, we skip it. Then, we pop room 1, mark it as visited, and process its keys, skipping rooms that have already been visited. Finally, we pop room 2, mark it as visited, and process its keys, which are empty. At the end of this process, all rooms 0, 1, 2, and 3 are in the visited set, so we return true. In terms of complexity, the time complexity of the solution is O, V plus E, where V represents the number of rooms and E is the total number of keys across all rooms. This accounts for processing each room and each key once. The space complexity is O, V, as we store the visited set in the stack or queue for traversal. These structures scale with the number of rooms, making the algorithm efficient both in terms of time and space. This solution implements a graph traversal approach using depth-first search, DFS, to solve the keys and rooms problem. The problem is modeled as a graph where each room is a node, and the keys represent edges to other nodes. We start by calculating the total number of rooms, n, and initializing a visited list to keep track of which rooms have been accessed. Initially, all elements in the visited list are set to false. We also use a stack, initialized with room 0, to perform the DFS. The while loop continues as long as there are rooms in the stack to explore. In each iteration, we pop the top room from the stack, current_room. If the room has not been visited yet, we mark it as visited by setting visited, current_room, to true. Then, for each key in the current room, we check if the corresponding room has been visited. If not, we add it to the stack for further exploration. Finally, after the DFS completes, we check if all rooms have been visited by using the all function on the visited list. If all rooms are accessible, the function returns true, otherwise, it returns false. This approach ensures efficient traversal of the graph with a time complexity of O, n plus E, where n is the number of rooms and E is the total number of keys across all rooms. The space complexity is O, n, for the visited list and the stack used during DFS. Here, we begin by defining our Java method canVisitAllRooms, which takes a list of lists as input, representing the keys available in each room. First, we determine the total number of rooms using rooms.size, and initialize a Boolean array called visited to keep track of which rooms we've already explored. We also create a stack, which will help us perform a depth-first search, or DFS, through the rooms. The process starts by pushing room 0 onto the stack, as that's the default starting point. Now, as long as the stack isn't empty, we repeatedly pop the top element from the stack, which represents the current room we're exploring. If this room hasn't been visited yet, we mark it as visited and then iterate through all the keys available in this room. For each key, if the corresponding room hasn't been visited, we push it onto the stack, effectively adding it to our DFS traversal path. This way, we ensure that we explore all reachable rooms and their keys in a systematic manner. After completing the DFS, we need to verify whether we've visited all the rooms. To do this, we iterate through the visited array. If we find any room that hasn't been marked as visited, we return false, indicating that not all rooms are accessible. If the loop completes without finding any unvisited rooms, we return true, confirming that we can visit all the rooms using the keys provided. This efficient approach ensures that we systematically check all rooms and return the correct result based on the accessibility of the entire structure. To solve the problem, we start by analyzing the input for example 1, where we have 4 rooms, represented as rooms equals 1, 2, 3. Initially, no rooms have been visited, so the visited array is false, 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 false. Our stack, which helps us keep track of the rooms to explore, starts with room 0, so stack equals 0. The goal is to visit all rooms and confirm if they are accessible. First, we visit room 0 by popping it from the stack, leaving stack equals. We then mark room 0 as visited, updating visited to true, false, false, false. Room 0 contains a key to room 1, so we add it to the stack, making stack equals 1. Next, we move to room 1 by popping it from the stack, leaving stack equals. Room 1 is marked as visited, updating visited to true, true, false, false. Room 1 provides a key to room 2, which we add to the stack, resulting in stack equals 2. Now, we proceed to visit room 2. We pop room 2 from the stack, leaving stack equals, and mark it as visited, updating visited to true, 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 false. Room 2 contains a key to room 3, so we add it to the stack, making stack equals 3. Next, we visit room 3 by popping it from the stack, leaving stack equals. Room 3 is then marked as visited, updating visited to true, 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 true. At this point, all rooms have been visited. To determine the result, we check if all values in the visited array are true. Since they are, the output for this example is true, indicating that all rooms are accessible. In example 2, we have a different input, rooms equals 1, 3, 3, 0, 1, 2, 0. Here, the total number of rooms remains 4, with the initial visited array as false, 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 and the stack starting with room 0, so stack equals 0. First, we visit room 0, popping it from the stack to get stack equals, and mark it as visited, updating visited to true, false, false, false. Room 0 contains keys to rooms 1 and 3, so we add them to the stack, resulting in stack equals 1, 3. Next, we visit room 3 by popping it from the stack, leaving stack equals 1. Room 3 is marked as visited, updating visited to true, false, false, true. Room 3 does not provide any new keys, so the stack remains unchanged at stack equals 1. Then, we proceed to room 1, popping it from the stack to get stack equals, and mark it as visited, updating visited to true, true, false, true. Room 1 provides keys to rooms 3 and 0, but since both are already visited, the stack remains empty, stack equals. After visiting all accessible rooms in example 2, we observe that room 2 was never visited, as indicated by the visited array, true, true, false, true. Since not all rooms have been visited, the output for this example is false, meaning some rooms are inaccessible. Lastly, in example 3, we have a simpler case with a single room, rooms equals. Here, the total number of rooms is 1, the visited array starts as false, and the stack begins with room 0, so stack equals 0. We visit room 0 by popping it from the stack, leaving stack equals, and mark it as visited, updating visited to true. Room 0 does not contain any keys, so the stack remains empty. Since all rooms have been visited, as confirmed by the visited array, true, the output for this example is true. This demonstrates that even with a single room, the solution works seamlessly. The time complexity of the solution is determined by the number of rooms and the total number of keys across all rooms. First, the initialization step involves creating a visited list of size n, where n is the number of rooms. This operation takes n time. Adding the initial room, room 0, to the stack is a constant time operation, O1. The main part of the algorithm is the depth-first search, or DFS, which uses a stack to explore the rooms. In the worst case, every room is visited exactly once, and every key in the input is processed exactly once. This means the loop executes O(n plus e) times, where e is the total number of keys spread across all rooms, effectively representing the edges in the graph. For each room visited, the algorithm processes all its keys, ensuring that each key is handled only once. Combining the initialization and DFS steps, the total time complexity is O(n plus e). The space complexity of this solution is primarily determined by the data structures used during execution. The visited list, which tracks whether each room has been visited, has a size of n, contributing O(n) space. The stack, which is used to manage the DFS traversal, can grow up to a maximum size of n in the worst-case scenario, such as when the graph forms a linear chain. This also contributes O(n) space. Additionally, the input list of rooms is not modified during the algorithm, so its storage does not count toward the auxiliary space used by the algorithm. When we combine these factors, the total auxiliary space usage is O(n), making this solution efficient in terms of memory. The time complexity remains consistent across best, average, and worst cases, but the structure of the graph determines how quickly the algorithm completes. In the best case, all rooms are directly accessible from room 0 with no redundant keys, meaning the number of edges, e, is minimal and equal to n1. Here, the time complexity simplifies to O(n). In the average case, keys are distributed randomly among rooms, and while the distribution may vary, the algorithm must still visit all rooms and process all keys, resulting in a time complexity of O(n plus e). In the worst case, the graph is densely connected, such as in a fully connected graph, where the number of edges, e, approaches n squared. Even in this scenario, the time complexity remains O(n plus e), but the number of edges can significantly increase the overall runtime. Thus, this algorithm is robust across all scenarios, maintaining the same asymptotic complexity. When comparing this DFS-based solution to a naive approach, the advantages become clear. A brute force method might try all possible combinations of keys to determine if all rooms can be visited. This would lead to an exponential time complexity of O(2 to the power of e), where e is the total number of keys, making it infeasible for large inputs. In contrast, the DFS-based approach avoids redundant checks by processing each room and key exactly once, achieving a time complexity of O(n plus e). Mathematically, this efficiency is justified because during the DFS traversal, each room is visited once, contributing O(n), and each key is processed once, contributing O(e). Since there are no nested loops or unnecessary operations, the overall complexity is linear with respect to the number of rooms and edges. This makes the DFS-based solution optimal for traversing the graph of rooms and keys efficiently without unnecessary computations. When tackling the keys and rooms problem, there are several common mistakes to watch out for. First, it's important to handle disconnected graphs properly. Many assume that all rooms are always reachable, but that's not guaranteed. You need to ensure all nodes, or rooms, are visited to confirm connectivity. Next, be careful with infinite loops in DFS. If you forget to mark rooms as visited during the traversal, you might end up with infinite recursion, especially in cyclic graphs. Using a visited set or array is a reliable way to track which rooms you've already explored. For BFS, a common issue is marking a room as visited too late when dequeuing it instead of enqueuing it, leading to duplicate processing and unnecessary inefficiencies. Another mistake is confusing room indices with key values. Since the keys might not correspond directly to room indices or could be out of order, it's crucial to verify the mapping between keys and rooms. Finally, avoid overcomplicating the graph representation. The problem already provides the graph as an adjacency list through the rooms list, so there's no need to introduce extra data structures unless explicitly required by the problem statement. This problem is an excellent test of your graph traversal skills, whether it's DFS or BFS. You should be able to explain the differences between these two approaches and discuss the trade-offs. Understanding when to use one over the other is a key part of the solution. Additionally, this problem ties into a broader category of graph problems centered around connectivity. Recognizing this theme will help you approach similar problems more effectively. Edge cases are another area to focus on. For example, what happens if there's just one room, or if a key leads to a room that's already been visited, or if certain rooms don't contain any keys at all? These scenarios often come up in interviews, so it's important to address them clearly. To deepen your understanding, consider related problems like LeetCode 200, which deals with number of islands, or LeetCode 547, which explores number of provinces. Both share the theme of connectivity and graph traversal. Another good comparison is LeetCode 994, Rotting Oranges, which uses BFS in a grid. These connections can help you recognize patterns and improve your problem-solving approach. Now let's talk about alternative approaches and their trade-offs. The most intuitive method is DFS, which can be implemented either recursively or with a stack. It's straightforward and works well for exploring the rooms, but recursion depth can be a concern for very large or deep graphs, potentially leading to stack overflow. DFS is another effective option that avoids recursion by using a queue. It explores rooms layer by layer, which can make it easier to understand in some cases. However, BFS might use more memory because you need to store the queue at each level of the graph. A less common but valid approach is union find, or disjoint set union. This method is particularly useful for tracking connected components in a graph. While it's an interesting alternative, it requires extra setup and might feel less intuitive for this specific problem compared to the simplicity of DFS or BFS. Each approach has its pros and cons, so the choice often depends on the problem constraints and your personal preference. Great job following along. To wrap up, we explored the problem keys in rooms, applying graph traversal techniques like DFS or BFS. We broke down the solution, analyzed its complexity, and discussed key takeaways. Remember to practice similar graph problems to strengthen your skills. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!